Dr. Rico here. This is a lecture from my course, System Dynamics. The syllabus link is in the description. Hey, Dr. Rico here. Today I'm going to tell you about computing eigendecompositions. So, computing eigendecompositions is rather straightforward with a numerical or symbolic computing tool, such as those available in Matlab or Python. The following sections show how to use Matlab and Python to compute numerical and symbolic eigendecompositions. And we'll begin with numerical eigendecompositions in Matlab. So, consider the following A matrix, or matrix that we're going to call A. We can define it in Matlab using the notation here. So, brackets gets us a matrix. If you use commas in between, that's preferable. You can also use spaces, and the semicolons denote that it's a new row of the matrix that you're defining. In Matlab, whenever you are going to continue on the next line with an expression, you have to use those 3 dots, so don't forget those. Okay, so we define it a 3 by 3 matrix A. We want to know what are the eigenvalues and eigenvectors of this matrix. We're going to use Matlab's function Eig, E-I-G. From the documentation, they say that if we use this Eig function, it will return, as long as we ask for 2 different outputs, it will return a diagonal matrix D, here in this position, of eigenvalues, and a full matrix V whose columns are the corresponding eigenvectors, so that the standard eigenvalue eigenvector problem is satisfied. So it's written in a bit of a matrix form. We would expect no less from Matlab, of course. So let's go ahead and give this a whirl with our A matrix. So we try using the Eig function on A. We ask for 2 outputs. If you don't ask for 2 outputs, it's not going to return 2 outputs. It has another default, but almost always if you want the eigenvalues, you want the eigenvectors. So you don't want to do that. So let's go ahead and display that with this command. I used VPA here just so that each of the output numbers is not a very long string. It's harder to read that way. So we'll take a look here, and we see that we get a display of VE, which is the eigenvector matrix that's returned. So each of these columns is an eigenvector. If you look, the first column here is real, right? All these numbers are real. So this is a real eigenvector. These 2 and 3 columns, the second and the third columns, have mixed real numbers, so the second component of each is real. But the first and last component of each is a complex number with non-trivial imaginary component. And so we've got complex eigenvectors here. And they always come in pairs when they're complex, and that's what we've got. The eigenvalues are on the diagonal of DE. Remember, we assigned the first output of Eig to the symbol DE. So if we display the diagonal of DE, as we do here, we see that we've got 3 eigenvalues. This real eigenvalue is the first one, and it corresponds to the real eigenvector above. They are always in order. So the first eigenvector in V corresponds to the first eigenvalue in D, and the second eigenvalue, second eigenvector, etc. And notice for a complex eigenvector, we end up with a corresponding complex eigenvalue. Okay, so these are the eigenvalues and eigenvectors of a numerical matrix in MATLAB. We can investigate a little bit further, and this is the case, that the eigenvectors are normalized to have unit length. You may recall that eigenvectors are only unique within a scaling factor. So if v1 is an eigenvector, then so is 5 times v1, okay? Any scaling of an eigenvector is also an eigenvector, and it's not linearly independent if you just have scaled it, right? So you can normalize these vectors however you would like. Matlab has by default a scaling that makes the length of each vector, or the norm of each of these eigenvectors, unity, 1. So let's just check that to make sure. We'll take the norm of all of the rows of the third column, which would give us the third eigenvector, and the norm computes to 1. Just to see. We could do that for the first eigenvector or the second eigenvector as well. We would see 1 as well as a result. Great. So now let's take a look at symbolic eigendecompositions in Matlab. Sometimes symbolic parameters in a matrix require symbolic eigendecomposition, especially when you're doing design. So in design, when you can pick parameters, working symbolically as long as possible is preferable. That's what we'll do with the symbolic eigenvalue eigenvector problem. Potentially, we're interested to see how different parameters in our design are going to affect the eigenvalues and eigenvectors. What we'll do is use Matlab and its symbolic toolbox. So the symbolic toolbox is one of the more popular toolboxes and one of the more readily available and less expensive toolboxes. So we'll use that. First, we'll declare some symbolic variables. Syms is the function, if you give it a list that are separated by spaces of different characters, these variables will then become symbolic variables, and you can use them in expressions without defining them, making those expressions symbolic as well. So what we'll do first is actually define a symbolic matrix. The syntax for defining a symbolic matrix is actually the same as defining a numeric matrix in Matlab. So you just place in the symbolic variables, and those symbolic variables tell Matlab that, oh, okay, A is then going to be a symbolic matrix, and it'll treat it as such. So we define AB0C to be the 2x2 A matrix, and printing it out, it just looks like this. If you hadn't declared that A, B, and C are symbolic, previously it would say undefined variable or function A, undefined variable or function B, etc. But since you've declared them as symbolic, Matlab will handle them just fine. So the function eig is what we're going to use again for the symbolic matrix. So this function is overloaded in Matlab so that if the argument that it's given is numerical, it'll do a numerical eigenvalue eigenvector problem. If you give it a symbolic A, which we're doing here, then the symbolic routine is called, which has a very similar syntax, and what it returns is very similar. We assign VE sim and DE sim to the names of the output of eig of this symbolic matrix A, and it returns again a matrix of eigenvectors. So eigenvector in the first column, eigenvector in the second column, and eigenvalues along the diagonal of the D matrix that it returns. So let's go ahead and take a look at those eigenvalues. A and C are the two eigenvalues, and if you were paying attention to the A matrix that we defined, it is an upper triangular matrix we could just read those eigenvalues off that diagonal. It's nice to start with a problem that you know the answer to, right? So that is how to find the eigenvalues and eigenvectors of a symbolic matrix in Matlab. Now let's switch gears. Let's switch gears to Python eigendecomposition, or eigenproblems, or finding the eigenvalues and eigenvectors. These are all synonyms. So in Python, we can again do numerical eigendecompositions, but we're going to load a couple packages to do that. So first we'll load the NumPy package. We'll give it the short name NP, very common short name for the NumPy package. And we'll also import from the linear algebra module of the NumPy package the linear algebra linalg module, and we'll call it LA, again another short name, so that we can easily use it in our code without it expanding too much. This is just for some pretty printing, these last two options here. So consider the same numerical A matrix from the section above. So we're going to do the same problem in parallel. So the Matlab version, the Python version. So create it as a numpy.array object. So the way to do that is to declare that you're creating a numpy.array object, and that what should go into this array are the following lists. A list of lists, the rows correspond to this second level and the columns are here. So I've arranged it sort of geometrically in the same way to show how NumPy is going to interpret that as a matrix. So the numpy.linalg module, loaded as LA, gives us access to the Eigen function. They named it the same thing in Python as Matlab did. So you call LA, the linear algebra module, .eig, and you give it the A matrix, that numerical A matrix that we just created. In fact, it's just a NumPy array. It's not a matrix object. It's a NumPy object, a NumPy array object, which is not exactly a matrix, but we can treat it as such in many contexts, and we do here. So we give it A, and it returns, again, two different values. So one is the eigenvalues object, and the other is the eigenvectors object. We're going to print these out and see what they look like using f strings. So the eigenvalues, again, come out to be a real number, -11, and then a complex conjugate pair of eigenvalues as well. Just as before. And the modal matrix has a real eigenvector, but notice that these 0 parts of the imaginary number show up here as well. It's good to check to see how big those are. In this case, we know that this has to be a real vector because the complex eigenvectors can only show up in complex conjugate pairs, so we aren't expecting to see any imaginary part. But it's good to check, make sure you didn't make a mistake somewhere along the way. So we get the same modal matrix that's returned. Note that the eigenvalues are returned as a one-dimensional array, not along the diagonal of a matrix as with Matlab. So there's a little bit of a difference there. So we could print out the third eigenvalue if we like. Remember that Python is 0 indexed, unlike Matlab. So if you want the third component of an array, you need to give it index 2, because the indices are 0, 1, 2. And we'll print it out in engineering notation. Here's our eigenvalue, the third eigenvalue, just to take a look at it a little bit closer. Now we're going to switch gears. We're going to go to symbolic eigendecompositions in Python, okay? Just to round us out. 4 quadrants here. Matlab, Python. We're going to do numeric, symbolic, okay? So here we go. We're going to use the SymPy package for symbolics, which is the most popular and excellent, really excellent symbolics package that Python has. So import SymPy as SP. Again, we've chosen a short name so we don't have to write out SymPy all the time. So that package will give us symbolic routines to use. So we declare symbolic variables. This is one way to declare symbolic variables in Python. There are several ways. I actually prefer some of the other ways, but I wanted to make it look as analogous to the Matlab as I could. So that's why I chose this method. So what we've done is declare that A, B, and C are symbolic variables. They should be treated as such. So now we're going to define a symbolic matrix A. A equals sp.matrix. So what this is a SymPy object. It has a special type of constructor in it called matrix. Unlike in Matlab, where we could just throw in some symbolic variables into an expression that could have been to define a matrix numerically, you have to explicitly tell Python that this is going to be a symbolic matrix. So there's a little bit of a difference, a little bit more work, but that explicit writing out of what you're telling Python to do frequently helps you not get too confused about what type of object you're working with. So it's a double-edged sword, the convenience of not having to expressly say what type of object you're creating. So we do the same one that we created before in Matlab, AB0C. Display the A matrix, and we see AB0C. So the SymPy.matrix class, this is a type of object in the Python SymPy package. It declares a class of object called matrix. Okay, it has methods eigenvals and eigenvectors. Let's consider them in turn. So a.eigenvals, this is how you call. So now A is a matrix object. It's an object of class SymPy.matrix. Okay. It has as a method the eigenvals method. If you call eigenvals on that matrix, it's going to return the eigenvalues. The eigenvalues are A and C, remember? These are the eigenvals. Now, it's a little bit strange because it's actually returning a dictionary. So a Python dict object. And a dictionary is something that has a key and a value, right? It goes key, value. So if you asked for an object in a dictionary with a certain key, it would return the value to you of that key. And you might wonder why didn't it just give it to us as a list or as a NumPy array or something like that? Well, there is something that's important going on about the values here. So the keys are the eigenvalues. The value in the dictionary corresponding to each of these eigenvalue keys is the multiplicity of the corresponding eigenvalue. So if A shows up twice, the multiplicity would be 2. So there are 2 different eigenvalues that have the same value of A. It would be 2 here for multiplicity. In our case, each of these eigenvalues has multiplicity 1 because they only show up once. This is the term that you have probably seen associated with this is repeated eigenvalues. And repeated eigenvalues create all kinds of interesting things mathematically. Their multiplicity in this return value of this eigenvals method tells you what the multiplicity is of each of these eigenvalues. The eigenvectors method returns even more complexly structured results. So we'll do the same thing, eigenvectors, and of course it's going to give us the eigenvectors. But it does it in a sort of strange way it's pretty, there's kind of a complex structure, so we'll unpack it slowly. So it's a list, so this outer bracket means it's a list of tuples. So these parentheses are tuples. So you might remember a double would be something that's like x comma y. A triple would be x comma y comma z. So a tuple is, an n tuple is more of them. So higher could be as many as you like. So a tuple is the general grouping in order of these objects. So a tuple is another type of Python object that comes up a lot. So we get a list of tuples, each corresponding to an eigenvalue eigenvector pair. Okay, so what it gives you, so if we'll look at the first one as an example. So it gives you eigenvalue as the first value in the tuple. So a is the first eigenvalue that's returned. That eigenvalue's multiplicity is next. So it has multiplicity 1. We already knew that because the eigenvals already told us that the multiplicity of a in terms of eigenvalues was 1. So that shows up again here. And eigenvector is the corresponding eigenvector, so the matching eigenvector for that eigenvalue. And that eigenvector is given as, unfortunately, it's a symbolic matrix function, symbolic matrix object that is inside of a list. And I don't exactly know why they put that list there. So if you'd like to extract your eigenvectors, then we can do that using the sort of slice notation that Python has available in it for selecting out values. So we can say a.eigenvects. That's going to return, of course, that same list of tuples, right? We're going to take, we want to find the second eigenvector. Okay, that's what we're going to try to look for. So in that list that it's returned, it gives us two different eigenvalue eigenvector tuples, right? So we want the second one of those tuples. So remember, Python is 0 indexed, so 1 here gives us the second eigenvector, or eigenvalue eigenvector tuple. And the eigenvector is the third value in the tuple. And finally, we have to unwrap it from the list that it shows up in, just the first value in the list. So the second tuple in list, the third tuple value, meaning that you have a tuple now, the second tuple, and now we're going to select from that tuple 1, 2, 3. We're going to select out the third tuple value and first matrix in the list. So that gives us this as the eigenvector, the second eigenvector, symbolically in Python. That's all I've got for you guys. Thanks for tuning in. I'll see you guys next time.